কালকে ফাঁকি দিয়েছিলাম, এর মধ্যে দিয়ে পড়ায় দিয়েছি তোমাদেরকে। আজকে আবার খাতা কলমে যেতে হবে। ঠিক আছে, লেখা ঠিক আছে, দেখা যাচ্ছে?
জি স্যার।
Okay, okay, okay. Now, let's again see permeability. Permeability, mu, or mu not, permeability mu. How permeability comes? The relationship between B is equal to mu H. So, this H value and B value is related with this permeability value. If, say, for example, mu is equal to 1, then B is always equal to H. Now, if mu is less than 1, then B will be the greater than H. If mu is less than 1, then B will be the greater than H. So how it possible? How it possible that the original field strength H is less than the field strength of B of the magnetic material? How it will be possible? If the magnetic material opposes the applied field, and if it is greater than 1, if mu is greater than 1, then H will be greater than B. If your magnetic material assists the H applied magnetic field. Now, how it happens? I told you yesterday. Say for example, this is a magnet. Say for example, this is a magnetic material, rather. This is a magnetic material, the North Pole and the South Pole. Now, these are the lines of forces. These are the lines of forces. These are the lines of forces from a solenoid. The field is H. These are the lines of forces. The field strength is H. Now, the B will be the black one. This is B. The black one is B. What is B? The field strength of this magnetic material. The field strength of this material. This is B. Now you see the lines of forces of B will emit from the North Pole and enters to the South Pole. It is like that. This is the convention. The lines of forces emits from the North Pole and enters to the South Pole. The direction is this. The direction is this. The direction is this. Now, field strength is always here. You see, the field strength is So what are the black ones? This is B, not the H. H is this. The blue one is H. The blue one is H. This is the H. So if we see here, this is in the air, and this is the magnetic material, and this is air. So if we see in air, in air, the the field strength of B, the black one, opposes the H. In air, B opposes the H. You see, H is in this direction and B is in this direction. So H becomes lesser than what it is originally it was. What originally it was, the value of H become less in the air. But if you see here in the magnetic material, you see the black one, the direction of black one is in this direction, and the direction of H is in this direction. So here, you see in the inside the magnetic material, H is assisted by B, and here H is opposed by B. So here, if you see, here it is mu naught. The permeability is mu naught, which is less than B. The permeability, say in here, the permeability is mu naught, and inside the material, the permeability is mu. Say mu naught permeability in here, and this is permeability of the material. This is permeability of the material. Now, if the situation is reversed, say for example, this is now your north pole, and this is south pole. If the situation is reversed, it is north pole and it is, say for example, south pole. Now what will happen? Then the lines of forces will come through this way. This direction will be reversed. This direction will be reversed. Let us draw. This is, say for example, B. This is B. Then the direction will be reversed. Say direction will be reversed. Say here also the direction will be reversed. And inside the direction, the direction is this. Direction will be reversed. Now, say for example, this is H. This is H. So now what you will see? what you see in the air, in the air, in the air, mu naught, it is in the direction of the, in the direction of the, of this. In the air, the magnetic field H is assisted by B. And inside the material, H is opposed by B. Inside the material, you see, inside the material, H is opposed by B. Say, inside the material, you see, the direction is in this way, and the magnet lines of magnetic field H is in this way, H is in this way. So, inside the material, the mu value will be less than mu naught, will be less than mu naught. Here, the mu will be greater than mu naught. Here, mu will be less than mu naught, and here, mu is greater than mu naught. Now, what will be, what is mu r? Mu r is the, your, what? Mu, mu by mu naught. Mu naught by mu, no? What was it? What was it?
Mu by mu naught, sir.
Mu by mu naught.
Mu by mu naught.
Mu by mu naught. Mu r is mu by mu naught. So, if you see in this case, mu is greater than mu naught. The mu value is greater than mu naught value. So, this value, this mu r value, this mu r value will be greater than 1 in the first case. And in the second case, the mu r will be less than 1. In the second case, mu r will be less than 1. Where inside the material, the lines of force are opposed by B. Where inside the material, the lines of force opposed by B, then the mu r value will be less than 1. And where inside the material, the lines of forces will be assisted by B, then the mu r value will be greater than 1. That means the relative permeability, mu r is the relative permeability. The relative permeability value will be greater than 1. The relative permeability value will be greater than 1. So, B is equal to mu H. So, mu is very much significant. Mu is very much significant. How? We will see now. Now, why this magnetic property arises? Why magnetic property arises? This arises, this arises due to two main causes. Two main causes, you know it. First one is orbital angular momentum of electron. Electron is moving around the nucleus. Electron is moving around the nucleus. We know anything when electron moves around the round in any substance, if electron moves round, if electron coils, then it will show the magnetic properties. Say, for example, if I pass current here, current means electron, flow of electron is called current. If I pass current here in this circular motion, then we get a magnetic, we get magnetic field. So when electron moves around the nucleus, we shall get magnetic field. How? In the direction of the axis of the movement of electron. This is called orbital angular momentum. And we also get magnetic field when electron spins around itself. When electron spins around itself, spinning of electron will produce the magnetic field. So in an atom, the magnetic property of an atom is the combination of both the orbital motion and spin motion of the electron. Is the combination of orbital motion and spin motion of electron. Of course, this is a summation. This summation is vector quantity. This summation is vector quantity because the magnetic field has both both direction and value. So we get magnetic property due to the orbital motion and spin motion of electron. Now we have seen that there are mainly three types of magnetism. One is diamagnetism, second one is paramagnetism, and third one is ferromagnetism. There are antiferromagnetism, and ferrimagnetism also. This antiferromagnetism and ferrimagnetism are the types of ferromagnetism. So we have three types of magnetic material. We have three types of magnetic material. One is diamagnetic material, one is paramagnetic material, and third one is ferromagnetic material. This ferromagnetic material can show antiferromagnetic property or ferrimagnetic property. So when a ferromagnetic material shows ferrimagnetic property, then it is called ferrimagnet or antiferromagnet. But it is the type of ferromagnetism. So what are the diamagnetic materials? What are the diamagnetic materials? The diamagnetic materials are the materials that opposes the applied field inside it, where the mu value is less than 1 inside the magnetic material. Inside the magnetic material, the mu value is less than 1. So what is the diamagnetic material? The diamagnetic material is that material that opposes the applied magnetic field inside it. So, when there is no magnetic field, there is no magnetic field, there is no H, the applied magnetic field H. There is no H. The diamagnetic material is not a magnet at all. So let us suppose say this is a diamagnetic material. This is a diamagnetic material. Nothing is there. Nothing is there when H is equal to 0. Nothing is there when H is equal to 0. But but when when if you apply a magnetic field in this direction, if you apply a magnetic field in this direction, then you will find some induced magnetism in this direction, opposite to the applied field. Opposite to the applied field. So the value of H will be less inside the material. The value of H will be less inside the material than the value of chi m is equal to mu r minus 1. So the mu r value will be less than 1. So the chi m value will be negative. The chi m value will be negative. Now, at first, why there is no spin? Because the spin of the spin of electron, spinning motion of electron is cancelled by another, and the orbital motion of electron also is cancelled by one. Orbital motion of one electron will be cancelled by orbital motion of another electron. So if there is a pair of electron, in an atom, then the orbital and spin motion of one electron will be cancelled by orbital and spin motion of another electron. So we do not see any magnetic properties in the diamagnetic material when there is no applied field. That means when there is H is equal to 0. But if we apply a magnetic field in this type of material, then the orbital motion of electron will be changed by some the orbital motion of electron will be changed by some way. For that change of orbital motion, you there is some a very small induced magnetic. It is actually induced magnetic. Induced means it is induced by H. Originally, there was no magnetic substances, or originally there was no magnetism in this diamagnetic material. Due to the induction of your H external magnetic field, you will get some magnetic field opposite to the applied magnetic field. This external magnetic field induces the motion of the electron, induces the motion of the electron. So it is called induced magnetic field, and this induced magnetic field, actually in the language of magnetic material, or in the language of magnetic property, this is called magnetic dipole. Magnetic dipole means a magnetic substance where north pole and south pole is there. A magnetic substance where north pole and south pole is there. So, according to the language of magnetic material or magnetic properties, originally the diamagnetic substance has no permanent magnetic dipoles, but it has induced magnetic dipoles. That means when you apply external magnetic field, then you will find some dipole inside the magnetic material which will oppose the external magnetic field by some extent, not a very much, not a large extent, by some extent. This value, say for example, mu r is less than 1. How much less? Say for example, 0.95. By some extent, 0.96. By some extent, not a very large extent. That is called diamagnetism. Now, if we see about the paramagnetic substance, the paramagnetic substance has permanent dipoles. At H is equal to 0, you will find, say for example, you will find permanent dipoles. Say for example, it is this way, this is this way, this is this way, this is this way, this is opposite this way, this is say for example this way, this is for example this way, this is for example this way. This is random. This is random. This is random. It is so random that every magnetic dipole cancel each other, and you will find a, a total magnetic moment 0. There is no magnetic moment. Total magnetic moment is 0. Here is also total magnetic moment 0. Here is total magnetic moment 0 at H is equal to 0 when no external field applied. Here is total magnetic moment 0. And in the case of paramagnetic substance, when H is equal to 0, total magnetic moment is 0. Why? Why? Because the magnetic moment are haphazardly arranged so that the magnetic moment of one atom cancels the magnetic moment of another atom. So there is, you see, there is a permanent dipole. There is a permanent magnetic dipole. You see here, there is a permanent magnetic dipole, but there is not any permanent magnetic dipole. Now, if you apply a magnetic field in this type of material, if you applied a magnetic field in this type of material, then it will arrange themselves, the material will arrange themselves such that they will assist the external magnetic field. They will assist the external magnetic field. They will assist the external magnetic field. Hence, we get a magnetic moment chi m, which is greater than 1. Here, the mu r value is greater than 1. Inside the magnetic material, what happens? It assists the applied magnetic field. The first type, we have seen the first type. Inside the magnetic material, it assists the applied magnetic field. And here inside the magnetic material, it opposes the applied magnetic field. So this is the first type. This type of material is paramagnetic material, where inside the magnetic material, it assists the applied magnetic field. Hence you get the chi m value, which is greater than 1. This is a magnetic material. Now, if you withdraw this, if you withdraw the H value, then again it will have no magnetic moment chi m value. It will have chi m value 0. So this is the paramagnetic substance. So in case of diamagnetic substance and in case of paramagnetic substance, both, before applying the external magnetic field, in both cases, there is no magnetic moment. The chi m value is 0. After applying the magnetic field, in the diamagnetic substance, the chi m value will be less than 1, and in the paramagnetic substance, the chi m value will be greater than 1, but to the small extent, not a very large extent. Now, what will happen in case of ferromagnetic substance at H equal to 0? In ferromagnetic substance, you will see the maximum of material is arranged, actually arranged, it is arranged towards one way. You see, it is arranged towards one way. What is the difference between paramagnetic and ferromagnetic? It is arranged haphazard way. Here it is arranged haphazard way. You see, it is in this way, it is in this way, it is in this way, it is in this way. But here it is arranged in one way. Before applying the magnetic field, maximum of the material, the spin of the dipole of the maximum material is arranged in one way. Maximum, not all. Maximum of the dipole arranged in one way. So you will get some magnetic moment. You will get some magnetic moment before applying the external magnetic field. Before applying the external magnetic field, you will get some magnetic moment. So what is the difference between para and ferro? In paramagnetic, you will not get any magnetic moment before applying the magnetic field. But in ferromagnetic substance, you will get some magnetic moment before applying the magnetic field. And when you apply the magnetic field, all of them will be arranged and will assist the external magnetic field. will assist the external magnetic field. Now, if you withdraw this H, then you will get some magnetic moment in ferromagnetic substance. So this type of ferromagnetic substances are the permanent magnets. This type of ferromagnetic substances are the permanent magnets, not the diamagnetic substances or not the paramagnetic substances are permanent magnets. The ferromagnetic substances are only the permanent magnets. And this type of ferromagnetic substances are most useful in our in our applications. Now, what are the antiferromagnetic substances? The antiferromagnetic substances actually they opposes the ferromagnetic substances. Say for example, uh, this is a ferromagnetic substance. Say for example, all of them are in this way. In presence of applied magnetic field, what happens? One opposes another. One opposes another. In presence of applied magnetic field, one opposes another. So you will not get any your magnetic moment. This is the antiferromagnetic property. Now, what will be the ferrimagnetic property? Say, for example, Fe2, Fe3O4. Can you remember what is the name of Fe3O4? Can you remember? What is the name of ferrosulfuric oxide? It is actually a it is actually a combination of Fe2O3 plus FeO. Now, this is a combination of Fe2O3 and FeO. Combination is such that this portion, the portion of Fe2O3 is 2 and the portion of FeO is 1. Actually, the ratio of Fe2O3 and FeO is 2:1. Now, this Fe2O3 aligns in this way. This Fe2O3 aligns in this way. And this FeO aligns in this way. So you will find that this way magnetic moment at this way, and you will find magnetic moment as this way also. But they will not cancel each other because Fe2H3, the portion of Fe2H3 is 2. That means the number of atom in Fe2H3 is higher than the number of atom FeO. So you will get a net magnetic moment. Say, for example, there are 10 number of Fe2O3 and 5 number of FeO. So 10 number of Fe2O3 has magnetic dipoles in this way at upside, and your 5 number of FeO in the downside. So you will get 5 number of FeO net resultant magnetic moment of 5 number of FeO. That is called ferrimagnetic substances. They are actually ferromagnetic substances, but their their field strength is actually lower than ferromagnetic substances. They are ferromagnetic substances. So ferromagnetic, antiferromagnetic, and ferromagnetic, they all are actually the same thing. Only direction is different. Sometimes their direction of dipole becomes different. So these are diamagnetism and paramagnetism. So in the diamagnetic substance, actually what happens, say, say for example, this is a diamagnetic material. Say for example, this is a diamagnetic material, and this is the lines of forces. This is the lines of forces of, say this is the lines of forces of H. H means applied magnetic field. What happens? It will go in this way. It will go in this way. And it will go. So they repel, this type of diamagnetic substance repels the applied the lines of forces of the applied magnetic field. Now what paramagnetic substances will do? They attract the magnetic lines of forces towards themselves. So their value, their permeability value is greater than 1. Their permeability value is greater than 1. This is the this is the your diamagnetic paramagnetic substances. Now, now what is the effect of temperature? What will be the effect of temperature? If you if you if you raise the temperature of a of a of the system or of a magnetic material, what will happen? What will happen? Say for example, this is a paramagnetic material or ferromagnetic material. Say for example, this is a paramagnetic material or ferromagnetic material. It The magnetic dipole is like that. It is assisting the applied magnetic field. Now what will happen? If you raise the temperature, then their randomness will increase, entropy will increase, their randomness will increase, and the alignment of them will be decreased. Some of them will go to this way, some of them will go to this way, some of them will go to this way. So if you raise the temperature and raise and raise and raise. At a point, the ferromagnetic substances will lose all its arrangements, all its regular arrangements. That means assisting towards your applied magnetic field, all its regular arrangements. So when they lose all their regular arrangements, there will be no more ferromagnetic material. The point after the temperature, after a ferromagnetic material becomes or loses all its regular arrangements, is known as Curie point or Curie temperature. Above Curie temperature, there is there will be no ferromagnetic substances. And for antiferro, that is nil temperature. That is nil temperature. So above nil temperature, an antiferromagnetic material will lose its antiferromagnetic behavior. Will lose its antiferromagnetic behavior. So if I plot a graph, of, say, for example, this is H, this is B, and this is, say, in air. So for diamagnetic substance, it will be less than mu naught. And for a paramagnetic substance, it will be like that. And your for ferromagnetic substance, it will be like that. This is for diamagnetic substance, this is for paramagnetic substance, and this is for ferromagnetic substance. Now, next, the next thing is domain and hysteresis. Domain and hysteresis. Actually, we require the ferromagnetic substances. If you want a magnet, you can magnetize only a ferromagnetic substance, not the paramagnetic or diamagnetic substance, because in case of paramagnetic and diamagnetic substance, if you withdraw the applied magnetic field, the diamagnetic or paramagnetic substance will no more show the magnetic property. but only the ferromagnetic substance. If you withdraw the magnetic property, it will show the magnetic property. So, so the ferromagnetic materials are more important for us. Now, in the ferromagnetic material, there are some domains normally. What do you mean by domain? Say, for example, this is a ferromagnetic material. This is a ferromagnetic material. So you will have some domain. You will have some domain. This is called domain. This is called domain. So in each domain, say for example, in this here it is like that. It is like that. It is like that. Here it is like that. And here it is like this. In a domain, all the dipoles are in the same way. In a domain, you will find all the dipoles are in the same way. The dipoles of the magnetic substances are in the magnetic dipoles are different from the electric dipoles. The magnetic dipole means north pole and south pole, and the electric dipole means positive charge and negative charges. So there is a difference between magnetic dipole and electric dipole, mind it. So in every in in every domain, you'll see the dipoles arranged in the same way, and this is called domain wall. This is called domain wall. Now what happens when you apply magnetic field in this domain? What happens if you apply magnetic field in this domain? If you apply magnetic field in this domain, this domain wall, this domain wall vanishes as as the magnetic field, applied magnetic field strength increases. This domain wall vanishes, and all the dipoles are arranged in the same way. The domain wall vanishes, and all the dipoles arranged in the same way. Say, uh, mm, if we see a graph, it will be difficult for me to draw. So this is a graph of B versus H for a ferromagnetic substance. This is a graph of B versus H for a ferromagnetic substance. If you increase the applied magnetic field, say this is applied magnetic field. If you increase the applied magnetic field, say for example, for this substance, for this ferromagnetic substance, there are 4 domains. This domain, all the arrows are in this side. In this domain, all the arrows are in this side. In this domain, all the arrows are in this side. And in this domain, all the arrows are in this side. You see, the domains are changing. You see, the domain walls are changing. You see here, the domain wall are at the middle of the circle. You see here, the domain walls are at the middle of the circle. Now, when field is applied, when field is applied field increases, you see the domain walls comes in this side. This is not in the middle. And you see here, this is not in the middle at all. And this is, you see here, and here that there is no wall, domain wall at all. And finally, here you will get the there is no domain wall. The full this is full one domain here, and the applied magnetic field, or the magnetic field of this material, ferromagnetic material, is in the direction of applied magnetic field. So originally, originally there are four domains, and if we apply magnetic field, if we apply magnetic field, then the domains will be vanished regularly. The domains will be very part by part. Here you see the field strength increases, the applied field strength increases, the domain vanishes. And here there is no domain at all. So this is the way of magnetization. Now, what happens in the ferromagnetic substance? Say, again we come here. Now, if we draw the graph again, this is H, this side is H, and this side is B. This is B. Now, for a ferromagnetic substance, the graph is like that. What is this point? This point is called saturation point. This point is known as saturation point. So what is saturation point? At this point, the saturation point is that point. At this point, all, you see, this is the saturation point. Here, this is the saturation point. At this point, no domain is there, and all the dipole arranged towards the applied magnetic field. If you increase the magnetic field, nothing will happen. You see, from here, if you increase the magnetic field, the domain wall comes from here to here. From here, if you apply increase the magnetic field, the domain wall changes. And from here, if you apply if you increase the applied magnetic field, this direction will change to this. But if you increase the applied magnetic field above this point, nothing will happen. That is called the saturation point. Why nothing will happen? Because it is just in the direction with applied magnetic field. The direction of applied magnetic field and the direction of a ferromagnetic material is same. So nothing will happen. This is called the saturation point. You see here B set. That means this is B saturation. Now, what will happen? What will happen if you mm, mm, now what will happen if you take out the applied field? Say for example, you want to take out the applied field. That means this is if you increase the applied field here and you want to decrease it, and you want to decrease the H again to towards zero, then it will not come back through this way. It will not come back through this way. It will come back through this way. It will come back through this way. So this is called hysteresis. This is called hysteresis. What is hysteresis? Hysteresis is that B is not actually the rate of decreasing is B is not decreasing in that way, in that rate. The 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 rate of decreasing H is not equal to the rate of decreasing B. The rate of decreasing H is much more than B. This type of decreasing is known as hysteresis. Now you see here, very important thing. You see here, at H is equal to 0, you will get some magnetization. You see here, you will get some value of B. So at H is equal to 0, that means if there is no magnetic field, the ferromagnetic material has the magnetic property. The ferromagnetic material has the magnetic property by this amount, by this amount. That is, this point is known as Riemannian. That is known as remanence. This point is known as remanence point. Now, when the magnetic moment of when the magnetization rather of a ferromagnetic substance will 0. When it will 0? It will 0 when it will come through this way. It will come through this way. So it will be 0 when the H is in the opposite direction. When you apply magnetic field in the opposite direction, then it will be 0. And if you again increase it, this will be a saturation point here, and this will again go by this way. This is called, this type of figure, this type of graph is known as hysteresis loop. This type of graph is known as hysteresis loop. This is a loop here. From here, it comes here and here, 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 here. This type of graph is known as hysteresis loop of a ferromagnetic material. Of a ferromagnetic material. So this is resonance point, and this point is known as coercivity. This point is known as coercivity. So in a ferromagnetic material, we started from here, and the curve is like that. But when we decrease the applied magnetic field, it will not come in the same path. It comes in the different path, and the value of B is less than the value of H. That means the B is lagging behind the H. B is lagging behind the H. This type of property is known as hysteresis. When one value is lagging behind the other value, this property is known as hysteresis. And then you will find a hysteresis loop in the for the ferromagnetic substances, and all the magnetism of a ferromagnetic substances are inside, you'll find are inside this loop. All the magnetism of ferromagnetic substance you will find inside this loop. That is called a ferromagnetic uh, mm, hysteresis loop. Okay, I think we'll stop for today.